RAID stands for Redundant Array of Independent Drives, or disks. RAID gathers individual disk drives into a cohesive drive set often called disk groups, from which virtual drives can be created. These disks can make one drive appear as many smaller drives, or several drives appear as one single larger drive. Companies choose to go with RAID solutions for their storage applications to obtain more reliability out of their systems and scalability. And it depends on the value that is placed on performance of the total storage system, the overall capacity, and the level of data protection required. At a deeper level, there are 4 categories to consider when deciding upon RAID levels: performance, data protection, degraded performance, and storage efficiency. The first category is performance, which is realized through disk striping. To improve performance, data is written to and read across several drives in the RAID group, and because of this, data can be read or written more quickly than when compared to a single drive. The second category is data protection. RAID controllers protect against data loss in the event of a hard drive disk failure. Data protection is achieved by writing redundant copies of data to disks. There are several ways to do this, but all will consume extra disk space and affect efficiency. Optimizing for data protection will, to varying degrees, come at the expense of performance. In the process of preventing data loss, RAID controllers will consequently create higher availability for the data saved. There are multiple implementations for data protection. In one instance, data is copied on multiple drives. In another, parity information is used to recreate lost data. The third category is degraded performance. RAID controllers use several schemes to protect data. The simplest is creating a complete copy where multiple writes are done concurrently. More complex schemes involve creating parity information for each bit of data written to the drives. If and when a disk fails, the data protection method will determine how much the system performance is degraded until the failed disk is replaced and configured. The last category is storage efficiency. Data protection requires extra space that will consume drive capacity, meaning some of the disk space purchased is not available for application use. Efficiency is measured as a percentage. It is calculated by dividing the amount of storage presented to the OS by the storage consumed by the RAID level. The simplest protection scheme, creating a complete copy, is the least efficient. Only 50% of the storage purchased is available for user data, whereas other schemes can be greater than 90% efficient. RAID 0, also known as striping, distributes data across multiple disks to improve speed. RAID 0 is somewhat of a misnomer in that RAID 0 is non-redundant. The R in RAID stands for redundant. Since data is distributed across 2 or more drives without any element of redundancy, failure of one of those drives will result in data loss. Let's examine an overly simplified RAID 0 configuration with 4 physical disks, A through D. Typically, there will be hundreds of blocks of data to be written. To simplify the example, let's assume that data to be written is 1 through 7. A RAID controller implementing RAID 0 will write the data concurrently to all drives for improved performance. Performance. RAID 0 is the highest of all RAID levels. RAID 0 performance typically scales with drive count. For example, 2 drives configured as RAID 0 will perform approximately twice as fast as 1 drive. With the addition of more drives, the performance will scale linearly until other system bottlenecks are encountered. Data protection does not apply in RAID 0 as there is no redundancy. Losing a single disk drive results in the loss of data on the entire RAID 0 array. If a drive fails, data has to be recovered from a backup source. Degraded performance does not apply with RAID 0. As an example, if 5 drives are configured in a RAID 0 array and any one drive fails, the entire RAID 0 volume will become unusable. Efficiency is the highest of all RAID levels. RAID 0 is 100% efficient. All drive capacity is available for user data. 5 2-terabyte drives equals 10 terabytes of available storage. The one-fail, all-fail nature of RAID 0 volumes actually increases the likelihood of system downtime and data loss. However, RAID 0's speed makes it ideal for some applications. Video editing and similar tasks often benefit greatly. If there are other copies of the source material, the infrequent failure of a system and the associated loss of productivity that goes with it are acceptable. RAID 1 uses mirroring, which simultaneously writes the same data to 2 drives, creating a mirrored pair. With this RAID level, you will maintain duplicate sets of data on both disk drives. RAID 1 performance is the lowest of all RAID levels. RAID 1 performance is similar to a single drive, as the reads and writes are not striped across multiple drives. Data protection is high. If one disk fails, the controller switches to the mirrored drive, which provides no lapse in user accessibility. These mirrored drives can be used to run the system while the failed drive is reconstructed. Degraded performance is at the highest rating. Since all of the data is written twice on 2 separate drives, if one drive fails, you experience no degradation. RAID 1 is the lowest efficiency RAID level. This is because you have to write everything twice. As an example, if you need 2 terabytes worth of data storage, you need to buy 4 terabytes worth of disk drives. You will get exactly half of the available drive capacity. Some applications also use RAID 10, RAID 1E, RAID 0+1. RAID 5 uses striping, similar to RAID 0, but creates redundancy by using distributed parity. Typically, a minimum of 3 drives is required to create a RAID 5 volume. Let's examine an overly simplified RAID 5 configuration with 4 physical disks, A through D. For each bit of data written, a parity bit will also be created and stored on another drive. This means that for any drive failure in the array, parity information will be available on the remaining drives to recreate the data. As data is written to each disk, a parity bit will also be written. For example, if a data bit is written to drive A, then a parity bit for this data will also be created and sent to one of the other drives, B through D. All parity information for drive A will be distributed to drives B through D. The parity for drive B will be distributed to drives A and C and D, etc. Spreading parity across the entire array is important for performance considerations. In the event of a drive failure, the missing data can be recreated by reading the parity from the remaining drives in the array. In our example, if hard disk drive A fails, its data can be reconstructed by reading the parity information from drives B through D. RAID 5 offers high performance. Read performance in a RAID 5 configuration is virtually as good as RAID 0, while write performance is slower due to the processing required to calculate parity. Data protection. Data protection and availability is good, but RAID 5 tolerates only one drive failure. Degraded performance is low. The RAID controller, upon a drive failure, needs to reconstruct the data set and does this by rebuilding the array using available parity information. This affects all of the drives since the parity is distributed to all of them. Efficiency is good. With RAID 5, you use one drive's worth of capacity for the parity information. This means that the more drives you use in the array, the more efficient it becomes. As an example, for a 4-drive array, it would be 75% efficient. But if you used 10 drives, it would be 90% efficient. Some applications also use RAID 50. In a RAID 6 array, it uses the same parity method for data protection as RAID 5, but creates 2 sets of parity for each data bit written. This allows up to 2 drive failures to happen without a loss of data. Because of the processing required for 2 parity calculations, the write performance is typically lower than in RAID 5. Overall performance is good. Read performance is similar to that of RAID 5 and RAID 0, but write performance is lower due to the additional parity calculations. Data protection. Of all the standard RAID levels, RAID 6 provides some of the highest level of data protection and tolerates up to 2 drive failures regardless of which drive is affected. Degraded performance is low, just like in RAID 5. The low rating is due to the complex parity calculations required when a drive fails. Efficiency is good using RAID 6. While lower than RAID 0 and 5, it is higher than RAID 1 or 10. 2 drives worth of capacity are set aside and used for redundancy. For instance, if you purchase 10 drives, 8 are dedicated to storage and 2 are set aside for redundancy, making it 80% efficient. Like RAID 5, the more drives you use in the array, the greater this efficiency becomes. To summarize the RAID levels, RAID 0 offers the highest performance and efficiency levels, but no data protection. RAID 1 offers high data protection and degraded performance, but performance and efficiency are at the lowest of all RAID levels. RAID 5 offers very good performance, good data protection, and efficiency, but degraded performance is low. RAID 6 offers good performance and efficiency while at the highest level of data protection.